di sesi webinar hari ini ya. Alhamdulillah sudah mulai berdatangan ya. Karena waktu yang sudah masuk ke jam 9 sesuai dengan jadwal, alhamdulillah saya akan coba membuka sesi pagi ini. Pertama-tama saya ucapkan Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera, selamat pagi, dan salam sehat untuk kita semua. Alhamdulillah hari ini atas nama Universitas Pembangunan Nasional Veteran Jakarta, Fakultas Teknik, dan juga bersama dengan pihak MTRES ya, salah satu perusahaan yang bergerak di bidang software, khususnya untuk software simulasi Simufek dan emisi software. Hari ini akan menyelenggarakan sebuah webinar ya secara umum dan juga diskusi mengenai simulasi yang lazim digunakan di dunia industri, khususnya industri manufaktur, sehingga kita bisa dapat mendapatkan gambaran dan pengetahuan khususnya dalam desain dan manufaktur di dunia teknik ya, di bidang teknik khususnya insya Allah. Baik, sambil menunggu partisipan yang lainnya untuk hadir, saya perkenalkan dulu saya Armansyah. Saya di sini membantu dalam lalu lintas lah ya aktivitas webinar hari ini dari sisi Universitas Pembangunan Nasional Veteran Jakarta, didampingi dengan rekan saya Bapak Dr. Damora Rakasiwi. Kami bersama-sama di Departemen Mechanical Engineering atau Teknik Mesin di Fakultas Teknik Universitas Pembangunan Veteran Jakarta. Selamat pagi Pak Damora ya. Terima kasih Pak bisa
selamat pagi Pak Arman. Selamat pagi Pak.
Salam sehat Pak Damora.
Ya, alhamdulillah sehat Pak.
Baik, terima kasih. Kemudian saya coba sapa dari pihak emisi software atau Simufek, juga mewakili pihak PT MTRES saya rasa ya. Saya sapa Mr. Trinitor Inigo. Good morning, Mr. Inigo.
You're on mute actually.
Okay.
Sorry, I was on mute. Okay, so good morning everyone. It's nice to meet you all.
Yes, good morning, Mr. Inigo. How are you? And where are you now? Are you in Indonesia or?
No, I am in Singapore. Right now in Singapore, and next week I will be in Jakarta. I have some customer meetings for 3 days. So I'll be in Jakarta, Cikarang, Karawang area, so where the industries are mainly.
Okay. Okay, so thank you very much.
Yeah. Yes. So thank you very much. So Pak Didi, can we start, or you wanted to give?
Yes. Yes, we just start a few minutes ago. First of all, I would like to introduce you, my colleague, Mr. Dr. Damora Rakasiwi.
Okay.
Also is in the same department in our university, University Pembangunan Nasional Veteran Jakarta, in the engineering faculty. So, and I would also like to call, first of all, Mr. Didi Budiarso. How are you, Mr. Didi? Good morning. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Perkenalkan saya Didi Budiarso dari MTAS Indonesia, representatif dari MSc Software, Simufek, dan Hexagon, Pak. Silakan Pak Armansyah untuk host, memanage webinar kita selama ini.
Alhamdulillah. Thank you very much, Mr. Didi Budiarso. Terima kasih. I'm glad to see you again in this very beautiful event for us, especially as an academician and also engineer. Saya rasa, are you okay, Mr. Inigo, if we talk in Indonesia?
Yeah, you can talk, but I am not familiar with the Bahasa language. So in case, me and my colleagues, so let me start first. So myself, Trinitar, so I based in Singapore office, and I take care of Singapore, Indonesia, and Philippines market for MSc business. Okay. So I am with MSc for last maybe 10 years now, close to 10 years. And together with me, my colleague Sandeep, so he is our Simufek expert. And so the today agenda is basically, I will start give you some introduction about MSc and couple of areas, where we are strong. And then I will hand over my session to my colleague, and he will talk more about the Simufek, farming, welding, mainly these two key areas. So in between, so we are going to talk in English. But if you have any problem or anything you are not understanding, please feel free to stop us. And of course, Park Didi and his team is there, and in case to any language support or something is there. Or in case if we are talking fast or some concept you are not getting, please raise your hand, and we have enough time and we can go step by step. Okay.
Okay.
So let me share my screen first.
Yes, thank you very much, Mr. Inigo. I think we can start our webinar today, and please share your presentation.
Yeah. So are you able to see my screen now?
Yes. So far, okay. Yeah.
Clear now?
It's okay. Yeah. It's very good. Yeah.
Okay. So now I'm not sure whether you heard about MSc software earlier. So if I can start from the beginning, so MSc software was founded in 1965, and one of the the flagship tool or the software we use is Nastran. So Nastran is a code which we created for NASA in 1965. So there are two professors from MSc, Dr. McNeil and Swelder. So both of them got an award from NASA to build finite element analysis code. Okay, so there is a division in NASA that's structural analysis, and that is where they developed this code in 1965. Those days, computer and PCs revolution started. And initially it was in Fortran language, and then it is C and other different languages. So we actually started our journey in 1965 with the NASA, and it's basically a spin-off of NASA, basically I can say. And so 1965, we are the only one oldest FEA code, finite element code, FEA analysis when it comes. So all the other people in the market, they all are in 80s, 70s, they started off, but we are the only one, we proudly say we crossed 55 years so already. So it started the journey from there, and then 1990s where the non-linear things comes in, and also we in somewhere in and 2000 the multi-body dynamics tool Adams, and so we went on acquisition of different companies under MSc, and you can see in 2009 and 17 Simufat, Cradle, Acoustic. So I'll have some other slides which talks detailed about each solution. And while we are doing acquisition from the years in 2017, there is a company, Swedish company, which is Hexagon Manufacturing Division. So it's a Swedish metrology device company, and they bought MSc Software, an American company, for close to $1 billion value. So that's how now we become a Hexagon company. Hexagon MSc has become a part of Hexagon. So Hexagon, they sell and they manufacture this scanners, like the metrology devices, the CMM coordinate measurement machines, and Acon scanner, laser scanner, blue light, or white light. So those kind of things they manufacture for a quality perspective. The manufactured component, how best is the quality is. Where in MSc we will come, before you manufacture, how we can simulate and how we can, virtually we can improve the product. So that's some brief history about MSc, how we started off. So this is the same thing in terms of milestone. Actually, we have mentioned. So the one which is talking today is basically a Simufat. We acquired this company in 2015. Of course, Sandeep will give more overview of Simufat, and especially on the welding side. But these all are, the kind of technology we got it. Now, if you see, starting from Nastran. Nastran is a general purpose finite element structural software, where you can see apply the loads, boundary condition, and see the stresses and deformation. And then Mark is a nonlinear solver, highly a nonlinear solver. And then Dytron is basically explicit dynamics, basically for your drop analysis, your crash simulation, and those applications. And Simufat is basically for metal forming, forging, welding, upsetting, or traditional manufacturing process simulation. Digimat is a tool which used for multi-scale material modeling, like plastics, reinforced plastics, engineering plastics, mold flow, the fiber orientations in the plastics component. So that studies mainly on the plastics and the material side, polymer side, composites. Then Actron is for acoustic and noise. For example, today noise also become one of the important criteria. So any product you manufacture or any product you get it certified by authorities or government. So noise is become a pollution today. So every product they have certain level of noise they need to be maintained in terms of decibel. So, for example, automotive engine noise or aircraft noise or any kind of noise you see. I mean, so we will able to simulate it virtually and modify it or improve the noise aspect of the product. So, which is Actron. And then CFD, Cradle CFD. So Cradle is again a Japanese CFD solver, which is there again from last 35 years now. And it's one of the leading CFD when it comes to accuracy point of view, because Japanese products are known for the quality and the accuracy. And then we have Virus. It is an autonomous vehicle. I think today in Southeast Asia, Singapore, Thailand, Indonesia, I think every countries are now going towards autonomous or driverless cars in a way, ADAS and the driverless car or the autonomous vehicle. So Virus is a tool for that. And then Adams, anything you say mechanism or motion kinematics, like you have a machine design elements, anything you have more than 2-3 components which is in an assembly setup, and you wanted to do the behavior of the whole assembly or the whole dynamics behavior, so that we call it Adams. So for example, the automotive chassis systems or even the subsystems like, suspension systems. So these kind of multi-body or motion induced. So this we will address using Adams software.
And robotics. robotics. For robotics.
Correct. So the robotics, okay, it is not here, but it will comes along with the Adams. So Adams plus EC5, there is an 1D multi-body dynamics tool, which is mainly used for the mechatronics, mechanical plus electrical machines, drives, and the motors, pumps, hydraulics equipment. So that is basically, when you talk about mechatronics, so that comes together with that. So it's a motion bundle. Basically, it's basically an Adams plus EC5. Okay. And the center one is, we are trying to create an Apex. It's a unified GUI, so which can, work with the multi-body dynamics today in Astron, and it's a very easy to use interface where, people find it. The learning curve is very, very less when compared with learning something new software, because this is, the kind of documents we have and the help files we have. One can, easily learn within 1 day or 2 days of time to set up the model, import the CAD geometries, and do the, the simulation in Apex. So basically, our concept is basically from materials, right from materials to fabrication and parts and assembly and systems. So all these products which I'm talking here. So again, that will, again boil down to the material modeling, whether the digimat, plastics, and all the alloys and those things. And fabrication, the way how you, manufacture, basically additive manufacturing or 3D printing. Then forming, cold forming, hot forging, then stamping, forming suits like stamping analysis, sheet metal stamping. Then parts wise, the Apex as a parts verification, and the detailed simulation basically. And then assembly, when it comes to assembly, the SimoFact welding and the joining and those things. And then the whole system level, the acoustic and the complete assembly or the system level also we can simulate. So this is a couple of examples here. And yeah, so basically the same thing which I talked about, structures and manufacturing. So that's the unified environment, we are trying to create, right, from autonomous CFD. So this is an entire MSc portfolio, but I understand from Pak Didi that, so you are mainly focusing on manufacturing solution. And again, in manufacturing, particularly you are keen on SimoFact building. Okay. So we will get deep dive into that. But in any time, even later also, if any of your professors or lecturers or students or researchers wanted to get more detailed on CFD area, or even this the structural side or acoustic side or material side, please feel free to reach me or Pak Didi. We will have a separate demo or dive-in session for that particular area, because these all are quite different vast area. So we can have a separate meetings. These all are a couple of examples in industry. So this is an industrial examples. So one is the tire simulation. The tire is a highly nonlinear automotive tire. So how this impact analysis on a tire, the interior metals and everything is modeled. And in automotive, again, it's an acoustic solution from automotive. Yeah, so this is you could have heard some noise there. That is actually simulated by our software for this Ferrari. So that this software will help you to will simulate the noise behavior of any system. It can be automotive or jet noise, or even UAV noises or things like that. And again, computational fluid dynamics. So aerodynamic forces, CFD, it can be an electronic fan cooling system, the temperature behaviors. And then this is an, the environmental modeling. See, for example, you have a tall buildings, and how this air consisted of the airflow or the temperature flow is happening around the building, and of course inside the building. So these kind of, the especially for construction and building and construction. So such kind of, many of the builders in Southeast Asia, they use a server tool for this. Okay. And yeah, then this is a material one. So, and this the last one is autonomous. So if you can see the truck, this truck is simulated using without any driver with sensors mounted on the cabin. So based on the sensor and the camera lidar perception, it will pass the information back, and then it will behave like a ADAS, automated driving system. So this is again from MSc Adams plus VTD combined tool. And then you can see the gearbox, where you have powertrain, the powertrain mechanism and gearbox and those things. So this also we have a solution for Romex. So that's all. This is a little bit, okay. So the virtual manufacturing, so which I talked about, the stamping basically, the tool, the development, and the blank and the fixtures and those things. So how to, material utilization, how maximum we can utilize, how to reduce the scrap materials. The scrap or flash material can save, a companies a lot of time in terms of revenue. And cost optimizer, how best you can, the tool designing side, how it can help the manufacturing companies to, build a tool like that in an optimal way. So this is all about my one slide, but I wanted to share another one set of slide. Just give you about before hand overing to Santi.
Okay.
So you have any questions so far?
Excuse me.
Yeah, any questions so far?
So far, yeah, very interesting information. But so far, I can see the MEC software, yes, such as Adams and Cradle and so on, which is also can be used for simulation and many things in engineering application, such as robotic, automotive engineering, and manufacturing, and so on. Yes.
So I'm sharing my slide again. If you see in
Sure.
Southeast,
Yes.
Are you able to
Please.
see my screen?
Yes.
Yeah, so this is basically just to show you, across over 500 universities in Southeast Asia. So even including universities in Indonesia, like, YTB and many universities are there. And then, over 10,000 universities across the globe, they are using MSc software. You can see in Australia, RMIT University, University of Michigan, NUS, NTU in Singapore, so almost all Nanyang Technical University. So if you see in over globe, or even in see here, you can see a couple of universities are from Thailand, Vietnam, Indonesia, and things like that. So these all are the things, when people are implementing and, adapting to build the skill sets for the students. When they come out of university, they are ready to get adapt to industry and the technology. They kind of use it in their projects. So this is one slide I wanted to talk, and these are a couple of logos. So over we have 10,000 customers who uses in Euros. This is in automotive. First one, you can see all the big names like General Motors, Nissan, Mazda, Tata Motors, Toyota, Volvo. So of course, even in Indonesia also we have Astra, Honda Motors, and many automotive companies. Then you see the aerospace companies, all the top OEMs like Boeing, Airbus, GE, Bombardier, Embraer, all these guys are using it. Even in Indonesia also we have PT Dirgantara, the new RAI, the regional aircraft project which started last few years back. So all these, when it's big, and Lapan, basically a satellite or rocket. So mainly, if I can say, because anyway we came from aerospace and space industry, and we are very strong in NASA background and the quality of results we produce. So that's why we are very strong in this area. And not only aerospace and automotive, you see any product, mechanical is there everywhere. You go electronics industry, of course there is a mechanic systems are there. You go civil, there is a mechanical structures and everything. So even in any energy, wind energy, like the windmill, again you have a power plant there, you have a transmission there. So you can apply it in any of these areas. Even for example, companies like Apple logo, you can see Apple, even Seagate, Xerox, and NXP. Delphi, so even automotive supply. So these all are a couple of logos to show you that, so we are, they are our customers. And again, so I'll just keep, there are so many things I can keep going on, even from aerospace. These all are aerospace guys, and these all are shipbuilding. For example, YKB, Class MHK, and even the Bureau Veritas, Lloyd Registrar. So these all, the ABS, Thales, so Aviva Marine. So these all are Mitsubishi. So these all are defense. And again, when it comes to defense, these all are defense or armed or weapon manufacturing companies. They use MSC tools, the BAE systems or General Dynamics and these kind of, and NATIC, those things. Then machinery companies like Caterpillar, Volvo, these all are, the Japanese like Kubota, Cosmi, these all are, the machinery guys, who manufacture like lift maybe, or, the special equipments used in mining industries. So these all are, a couple of guys. Now I come to this. Okay, so this is the, much more simplest way of, showing strength analysis of, so this is basically an atoms. You see the motions, kinematics, more than 3-4 components are connected with the spring. So anything related to this strength or, motion, we call it atoms. Then you see the farming, manufacturing, vehicle dynamics, the vehicles are running in test track, and, seeing the stability of the automotive chassis or car. Then this is a case of NASA, the Curiosity rover landing. The sequence by sequence, they used our atoms to predict that, because it has to be very critical. It has to dismantle, and it has to, each subsystem has to work within timeline. And these things, they cannot do any prototype, because it's a very critical application, and sometimes you cannot have a prototype. So these all are the areas of application, MSc is there. And again, building the bridge between academic and manufacturing is another area. You can see there is a gap of, the applying math, science, and engineering. So that is where, the 98% gap is there. And that is why we collaborate more with the industry-oriented R&D focus with the colleges, universities, and academics, so that, they will get the real-life applications within the real-life tools. And so that, the people will be, able to get a job, or, the country's economy and everything, they are driving through this engagement, basically. Now I'll just keep this slide, and I'll just go to straight away to these are a couple of universities. They adapted in their syllabus and curriculum. And another one is some of the student competition, basically, your SAE, Baja, and those kind of competition we offer licenses. Now there is a course material we have recently developed. So basically, this is one of the sample course content. So for example, you would have known this textbook, the design of machinery, which is written by Norbert Nolten. And many of the universities, they prefer this one during their third semester or fourth semester. So what we did is, our couple of our university professors in US, they took this textbook, and they created some material, like tutorial and workshop, and some exercises. And the morning they teach in the like a cam and follower, or kind of the topics. And we created a supplementary toolkit. Okay, so afternoon in the laboratory, they go computer CAE lab, they will go and they will simulate. Morning they will follow this cam and follower, or 4-bar mechanism, linkage mechanism. This is it can be applied in mechanical design, dynamics, robotics, and many machinery courses, like where you have a gear train, pulleys problems. All these problems are referred in the textbook, and we have created a sample and compared the result. These all are couple of this is a 4-bar link mechanism. So this we have done, and then this is mapping the syllabus, basically your material science and metallurgy, TTT curves. So we use Mark and Regiment for this. Thermodynamics problem, we use Mark again for this. Again, mechanics of materials, stress strain curve, we use text. Then manufacturing, like foundry and welding, casting, molding, various type of welding, like soldering, bracing. So all these areas, when the professors or the lectures teach in the semester 3 or 4, I'm not sure, in mechanical engineering, and we use the SumuFact or respective softwares from MSc. They will use it in the laboratories. These all are couple of examples like molding, the glass molding, casting simulation, piezoelectric actuators, MEMS, and then fluid mechanics, for example, buoyancy or fluid. This is another semester things. We use Mark SumuFact and this is. So this is a die design, one of the die design simulation we do. So these are a couple of examples I can just show. So like this, we can go on like, the fourth semester. And then this is on the fourth semester. So in fourth semester, you can see the engine dynamics, the piston and engine, how it is, gear train. So metal cutting, for example, manufacturing the metal cutting simulations. Creep and fatigue. So this is on semester B basically. So like this, we can keep going on. I will just this is an impact study. Then this is a wind energy. Of course, you may have energy in a couple of your semesters. The camp follower mechanism. So how we are teaching in the theory, in the classroom. So how we can riveting, rolling, chain, assembly line. This is again, the robotics of, picking and placing robot, that trajectory. This has not only mechanism, this has a mechatronic system because, it uses some pneumatics or motors to trigger the motion and things like that. So like this, so we have every semester, like this is 7th semester. And robotics, basically climbing robotics on a stair, shock waves, bending. So these all are a couple of examples. Our students, they use it in the engineering divisions. So that's all. So this is one way, how we can. This is 3D printing, the last one. So now I will. So basically, what we do or what we. This is one slide which I wanted to focus. There is a specific industry like automotive, aerospace in the market or in the country. There is something like universities or academics, and see these universities will. Industry will recruit students from universities. But at the same time, industries will give a project or research to universities. So there is a, the two way of mutual interaction should happen, and it is happening. And where we belongs is, our MSc products at the bottom, where we supply to university, we collaborate with the industries, so that, so when these students exchange happens between university and industry, it will be a, common platform or common technology or skills development and, all those things. So that is where the academy to supply the enough manpower to the country. So with this, I will conclude my presentation. You have any questions on this topic, and you please feel free to raise a question. And I will hand over my session to Sandeep, and he will take you more detailed on welding and maybe a demo if he has enough time. He will show you a simple problem how to set up or how to show that results. And then you feel free to ask any capabilities or any features or anything you are particularly looking. Let's discuss on that. Okay. So thank you very much.
Okay, thank you very much, Mr. Inigo. Very interesting information that we can have from your presentation. Realize us that a simulation is very important, especially in engineering field, to accommodate any ideas and solution in engineering problems. So, okay, itu tadi hasil dari pemaparan dari Mr. Inigo dari MSc Software dari Singapura. So, bagi siapa yang ingin bertanya, saya persilahkan. Sekarang sudah masuk sesi bertanya. Silahkan memberikan informasi atau mengacungkan tangan apabila ada pertanyaan. Silakan.
Okay, should I start? This is Sandeep.
Oke. Kalau begitu kita persilakan Mr. Sandi untuk melanjutkan sesi presentasi ini ya. Baru nanti kita tambahkan dengan sesi pertanyaan. Okay, Mr. Sandip,
Okay.
please your time now. Thank you.
Okay. Thank you. So, good morning, everyone. Thank you for your time today to present our capabilities. So I will share my screen, and if you have any questions, please do let us know so I can answer those questions. Okay. So I'm. Can you see my screen? Can you please confirm?
Yeah, we can see. Maybe you go to the present. Okay.
Okay, great. So my name is Sandeep Manurkar. I'm a senior technical specialist. So I did my master's in Germany, and I was working there with a company called SMS Mir. And for past 9 years, I'm working with MSc software and mainly working on the SIMFACT products. Okay. So today I'm going to present the capabilities on the SIMFACT welding side, which is very dedicated for all the welding applications. It will do the simulation and will help you out in the finding out the distortion stresses, different kind of results from the software. Okay, so we'll go in detail about the SIMFACT welding software. Okay, so as Triniter explained this slide, actually the SIMFACT is a part of the MSc software. And MSc software is now part of the Hexagon group, which has a different products, right from the metrology till simulation softwares. Okay, so SIMFACT is a manufacturing division of MSc software. And this is the history of the SIMFACT welding software. Okay, so all these companies, BMW, Mercedes, Porsche, Volkswagen, Audi, all these companies came together and given an order to SIMFACT to develop and software for their particular welding application. So SIMFACT developed that software and tested in their shop floors. Okay. Since they have invested in our software, it was exclusively used for them from year 2005 to year 2012. After year 2012, it was available for everybody. And by year on year, we have added a lot of capabilities like resistance spot welding. We have improved our solver, meshing capabilities. In the last version, we added this direct energy deposition method, which is kind of a additive manufacturing process. And this is a very hot topic area right now in the academics as well, that this DD. And it includes the processes like WAM and the layer by layer addition. The last variation, this latest variation is that SIMFACT welding 2021, which has Python interface, okay, and a lot of capabilities along with it. Okay. So normally the welding simulation, okay, it basically divides into 3 areas. First one is the process simulation, where we study the fluidity of the molten material. So when you're doing the welding operation, the material melts, right? And it flows. So that comes under this process simulation. Second is the structure simulation, where we study the global temperature field, basically the heat affected zone, the temperature gradients, the residual stresses. These are very important because if the stresses are very high, then the component might fail at that particular location. So those stresses are important. The structural behavior and the distortion. So all these kind of results comes under the structural simulation. Under the material simulation, we can study the results like the phase transformation, basically how much is the martensite, bainite, perlite, all those we can see it. Also the hardness. The SIMFACT welding can do structural simulation and the material simulation. The third part can be done by the CFD tool. Okay. Now we'll see some of the potential benefits you can get it from the software. Okay. First and foremost thing, it helps you to replace the tryouts. Okay. So what it does, whatever you're doing it on the testing lab or the shop floor, we replicate the same thing on the software and we'll give you the output. Okay, it can help you in the 2 stages, design stage and the manufacturing stages. So you can verify your design, you can identify problems like the distortion, the stresses, you can also test new designs. Okay, manufacturing process, you can investigate manufacturing problems, you can get in looks inside into your process. Like there are a lot of parameters which can influence the total product quality or the weld quality. Those things you can study it in detail. Also you can optimize process, you can optimize the weld sequence, you can optimize the fixtures, you can optimize the heat source, current voltage, these things. The main output from the SwingFacts welding is to find out the distortion and the stresses. You can study another potential benefit is that you can study the influence of different weld sequences. For example, over here, we have 2 sequences. In the sequence 1, there is a side-to-side welding. And with the numbering, you can see this is the first weld, this is the second weld, third weld, and fourth weld. Okay, like this. For this type of weld sequence, what is the distortion over here is that 1.37 and 1.04 mm at this particular location. Okay, when we change the welding sequence to counterclockwise, so first here, second weld here, third and fourth over here. So with this welding sequence type, we got the distortion of 0.67 and 0.75. Okay, so you can see that distortion is pretty much lowered it down. Okay, so you can see the influence of those welding sequences on your component distortion. Okay, another way is that you can study the influence of different weld paths. So basically we have 3 welding sequence, 3 welding paths. Okay, first one is the continuous weld, second is the kind of intermittent welding. So okay, there is a gap between the 2 welds, and there is a third one that is kind of a side-to-side welding. Okay, and with the percentage form, we can see that for the last variation, we have less distortion or the stresses. Okay. Also, you can study the influence of different thermal truing sequences. So we have 3 variants, and yellow arrows you will see. This yellow arrow is nothing but it shows that this is my starting point of the weld and this is end point of the weld. Okay. Similarly, for the variant 2 and variant 3 is shown over here. Okay. So this is an example of the coupling jaw carrier, the commercial vehicle component. Okay. And so this is the output. This is my distortion values. So it ranges from 0 to 2.60 mm. And you can see that for the first 2 variants, these plates are bending on the outward side. Okay. It is bending outwards. And for the last variant, there is a very, very less distortion. Okay. So with the color coding, you can see that where it belongs, this distortion range. Okay. So I can say that for the variant 3 is for my good process and I can go ahead with it. Also, you can study the influence of different clamping positions. Also, you can add the clamp forces also. Okay. And this is the components. The green and the blue one are the components, and the small cylinders you see over here are nothing but the clamps. Okay. And with this clamping type 1, we have distortion of 1.77 and 2.73 mm over here at this particular location. After seeing that result, we added one more clamp at the central location. Okay, over here. And with this clamping type setup, we are getting distortion of 0.72 and 0.85 mm. So this way we can study the influence of different clamping position. Okay. Also, we can help you to, it helps you to in designing the process, basically the design of experimental study, which academics is needed. Okay, there are a lot of parameters which influences the product quality or the weld quality, like welding direction, welding sequence, pre-bowing or the pre-bending, the number of welders or the robots, the heat input, basically whatever the current, voltage, okay. And there are a lot of variations are there, okay. Lot of means 23,000 kind of combinations we can do it with using these 5 parameters, okay. So we took the 4 probables from this one, okay. And for these variations, we did these are the inputs, like there are 2 robots are working, what is the pre-bending, voltage, current, and the torch velocity. And as in distortion, for the last variation, we got the less distortion. And with this way, we have optimized the complete process, okay, and come up with the perfect parameters. So we can do this kind of a design of experimental study, okay. So as of now, we have seen what the potential benefits we can get. Now we'll see some of the case studies, okay. So first one is the motorcycle swing arm, okay. So this is a typical shop floor setup over here, includes the fixture, the clamps, this is the component, okay. And this is the micrograph you can get. So it shows that how much area has been melted during the welding operation. So you can see over here, okay. And this is the output of the software, that it shows that maximum distortion happens basically in this area, okay. And this is the comparison of the experimental weld pool and the simulation weld pool. So with the given heat input, the current voltage, how much is the weld pool has been generated, we can see it over here. And this is the comparison of it. So we can see that we accurately predicted that one. And in this case study, we are optimizing the heat source, okay. So earlier we used the heat input of 4,100 watts, okay. With this heat input, we were getting this kind of weld pool, which was having the large weld penetration and the substantial overwelding was happening, okay. So then what we did, we reduced the heat input from 4,100 watts to 2,000 watts, okay. And with this heat input, we got just sufficient weld penetration and no overwelding was happening. And with the reduction in heat input, the distortion also got reduced. Next example is inner door assembly welding. It includes the laser welding, okay. So this is an Audi car door example, okay. There are 3 robots are working at the same time. For each robot, the welding sequence is shown over here with these lines. So for example, so for robot 1, this is the first sequence and it goes from here to here. Second sequence for robot 1 is from here to here, okay. Similarly, for the robot 2 and robot 3 is shown over here with these arrows, okay. And this is the comparison of the simulation result versus shop floor result or the experimental results. So we can see that it is pretty much accurate over here, okay. Another example is the roof raising operation. So this is a car top body, okay, and the section you see over here, this is the brazing operation happens. So basically the metal gets deposited over here, okay, in this particular area like this. And this is just to show that with a small change in the input parameters, how is it is changing on the output, okay. So we have 3 different things. One is without holes, one is with the holes, and one is punching after a brazing operation. And you can see the the variation in the result as well, okay. Another example is the B pillar welding. So in the animation you can see this is the welding operation happening and this is the temperature result, okay. How is the temperature is generating during the welding operation, we can see. And this is the distortion. So this is the area where the high distortion is there. You can see that it is about 2 mm over here, and this is the back side of it. So another example case study is that from the Folman group, where we have included the forming history also. Okay, so as Trinitor explained, we have the SIMFAT forming software also. So this is my final component. Okay, to form this component, there are 11 forming stages are there, like coining, cutting, stamping, and the bending operation, like these 11 forming stages. And we take the results from one stage to second, second to third, third to fourth. Like this, we take the history and this is the final output of this. And you can see it in this animation. This is the bending operation. So this is my component. This is my pressing tool, this one. Okay, once it pushes that one and get released, you can see there is a small spring back is there. Okay, so we can accurately predict the spring back, okay, with the software. And then from the forming, we take the results to the welding operation, and you can see it in this animation that welding operation is happening. And we have the two cases. One is without forming and one is with the forming history. So you can see this blue one is with the forming history and the red one is without forming history. So you can see that when we consider the whole process chain, and we'll get more and more accurate results, and we can provide those. Another example of the forming plus welding simulation is that, so this is the tube forming and this flat sheet is passed to the roller. So this is a rolling operation. We can do it in the SIMFAT forming. So this is the cross section of it. Okay, you can see that how it is. The rolling operation is happening and creating a circular tube. Okay, and then we take it to the welding software, and we can see this, the welding operation is happening over here. And we can see the different results like distortion, stresses, and the temperature distribution. Okay. Next example is that for the resistance spot welding. So this is the Jetta car example where we are doing this spot welding operation. So this is the B pillar of the car, basically situated over here in this car. And these are the fixtures, and you can see the temperature result during that. Okay. And this is the distortion result and the stresses. So you can see that the high stresses are being generated over here. If the stresses are beyond the limit, the component will have either crack or damage, kind of defect it will showcase it to you. Okay. Next example is process optimization and the fixture weight reduction. Okay, so this is a two-wheeler assembly, the bike, and the components include the support and the wheel house, and this is the welding area. Okay, and this is a typical shop floor setup. On one stand, the robot is doing the operation or the manual welding, and on one stand, the operator is loading the components. And this is how it looks like on the fixture. So you can see this, the green and the red one are the components, and the rest of the things are the clamps. Okay, so there are total 7 clamp towers are there. Okay, and the total weight is going around 279 kgs. Okay, and then we see the different results, the temperature, the phase transformation, basically the martensite formation, whether it is happening or not, in the spots, the stresses, and the distortion. So after seeing that, we reduced the 2 clamp towers from the fixture setting, okay, and adjusted the position of the clamps. So total weight was around 279 kgs. So after removing those clamp towers, it comes around 211 kgs. Okay, and before removing those clamp towers, the high distortion was happening in this zone, and after removing those, we can see that there is a less distortion. So fixture weight got reduced by 25% and distortion by 70%. So next thing I wanted to showcase that we have this So I wanted to showcase one case study on the welding sequence optimization using artificial intelligence or the machine learning. Okay, so we have a tool, WSO. It's mainly for the arc welding application. Okay, so what it does, so if you have any welding sequence, okay, and you want to optimize that, you don't know which welding sequence should be there to have the minimum distortion or the stresses. Okay, so with the help of artificial intelligence or machine learning, we can predict that what should be my welding sequence. Okay, so this is the case study. This is the cap floor. So there are some 117 weld bits are there, 12 components. Okay, so this is a WSO modeling. So this was the original weld sequence was there. Okay, you can see over here, this welding is happening over here. Okay, so some 117, and our software predicted the optimized the weld sequence, and it takes only 10 to 15 minutes. That's it. So within 10-15 minutes, you will get to know that what should be my welding sequence to have the minimum distortion of the stresses. So with the original, you can see this was the high distortion was there. So it was beyond 7 mm. And here it is with the welding sequence optimizer, we are getting the distortion below 4 mm. Okay. So again, this is the from the bottom side. So after unclamping, so this is, you can see that there is a less distortion over here. And another case study is on the mountain bracket. Okay, so this was very important because the components should get in the within the tolerance to get the fitment. And earlier with the original weld sequence, the lot of rates are there. It means these are out of the tolerance values. And when we predicted that say weld sequence and do the welding, and we can see that everything is in the grain zone. So it means it is within the tolerance levels. Okay, so up to now, what you have seen is case studies for the manufacturing side or this one. Now the case studies is for example, if you want to take these manufacturing effects into your normal C process, or you want to do the structural analysis or the fatigue analysis. Fatigue analysis is nothing but you want to calculate the life of that component or the welds. Okay. So first example is that the crash box. Okay, so this is a typical location of the crash box, and these are the different shapes of the crash box. And after impact, this is how it looks like. Okay, so the first operation is the rolling operation. So the flat sheet is passed to the rollers, and it is creating kind of a U shape of the tube. Okay, then we transfer it to the welding operation. And you can see this welding operation is happening. So this is my base plate. These are the fixtures. And as an output, we get the stresses and the distortion. And this is the crash test we did. In one case, we have considered all the forming and welding history. And in one case, we have not considered any history. So you can clearly see that the location of the distortion is totally different. And the graph showcases that the absorbed energy by the crash box during that crash test, you can see there is a clear difference is there. Now we'll see the case study for the fatigue analysis. So this is ongoing efforts by the SAFT and E committee to understand the weld-induced residual stresses and effect on the fatigue life of the component. So it will showcase that after how many cycles this component will fail, or the damage or the crack will happen. Okay, under the operating conditions. So this is a standard making company. Okay, so there are 3 stages in this particular process. First one is the welding simulation, second is the structural analysis, and the third one is the fatigue lab simulation. So we transfer the results from one stage to second to third. Now we'll see what detail one by one process. So this is the macro graph, showcases that there are total six welds are there. 3 on each side, and the numbering showcases that this is the weld sequence. First weld here, second weld here, third here, fourth, fifth, and sixth. Okay, and with this we are getting this kind of macrograph. So for these 6 welds, we are having these inputs like the voltage, current, the wire speed, the torch velocity, the torch angle, the cooling time between the 2 welds, basically. Okay, and with this setting we are getting this kind of weld pool, and when we compare it with the micrograph, it has come up perfectly. And this is the test results, and we can see that the red area, it means that the highest zone is there. The highest stress area is near to the weld, and the component might fail at this particular zone. Okay, and this is the distortion, so it is bending towards the left hand side. This black arrows, black the lines you are seeing, this is the initial position of the component, and this is the output final position of this one, this colored one. Okay, and this is a clip section of that one, so it showcases that this is the very high stresses are there. And then we take it to the loading simulation load. Okay, so this is the shop floor setup, and this is the model setup in the this MSC mark, and we are applying the load over here, particularly over here. Okay, and we have a load of 24 kN and R value of 0.1, and we can see the stresses over here. And then we transfer the results to the fatigue software. We have this MSC fatigue or the CAE fatigue, in which we see that with a load of 24 kilonewton and R value of 0.1, we have calculated the simulated life as 47,700 cycles. So after these many cycles, the component will fail, or the crack will or damage will happen in this particular area. Okay, and this is the comparison with the shop floor setup. So for 24 kilonewton and R value 0.1, we have mean of the test data and max of the test data. And when we take the average of these two, this mean and max, it comes around 50,000, and the simulated life comes around 47,700 cycles. So it pretty much predicted very accurately in the software. So this is my last slide. So SIMUFAT has 3 softwares. First one is the SIMUFAT forming, in which we cover all the forming processes, right from cold forming, hot forging, sheet metal forming, mechanical joining, pressure welding, rolling, ring rolling, open forging, and heat treatment. So these are the main modules comes up, and under those main modules, there are different sub processes are there, like the upsetting, bending, heating, all those sub processes comes around in those modules. Also, we have second software that is for the additive manufacturing simulations, which covers the powder-based fusion and the metal binder jetting. So we have just released in this week the newest version of the additive, where we can do the machining operation as well. Okay, and we have the SIMUFAT welding, in which we cover all types of welding processes, be it arc welding, laser welding, electron beam welding, resistance spot welding, brazing, stress relief heat treatment, and this is the direct energy deposition, which is very famous in the currently in the all the academics, as we see all over the Asia and Australia and India, all over the world. We see that this is this is the interesting topic for all the academics. Okay, so what we have seen today is that how is the welding software can help you in doing all the research. It can help you in doing the design of experimental study. We have seen the different case studies for that one, and also how we can incorporate the forming results into the welding operation. So total process and how we can simulate, and also if you want to do the structural analysis or the fatigue analysis, that also we can do it. So it is pretty much we can cover the whole process chain for the academics and for the industries. Okay, and if you have any questions, please let me know. And Trini, how much time we have still?
Yes, we still have time.
We have another 20-25 minutes.
Okay. Then I can show the software demo also.
Yeah, so maybe a
How it
simple
works.
problem.
Yes, yes, please.
Okay. Thank you. So this is my, when I open the SimFat welding software, it comes like this. Okay. So I'm going to show you what input parameters are required, how it is easy to do the welding process. Okay. So I will create a new project. Then it asks what type of process type it is, whether it is arc welding, laser welding, brazing, spot welding. So you can choose accordingly what process you have. So for demo purpose, I'm taking the arc welding operation. This we can set up the ambient temperature. So ambient temperature is okay. Also we can define the gravity. And there are some parameters are there, like the components to be get welded. The bearing is a part of the fixture. Okay, so it's kind of a base plate. Then fixed geometries, fixed nodes, other type of boundary conditions. Clamping, as the name suggests, it is a clamp. Local joint is nothing but for the tack welds. And robotic, whether it is a robot welding or the manual welding, we can specify those. So I will just specify those things. One bearing, 2 clamps, and 1 robot, and say okay. As soon as I say okay, it has opened 3 GUIs over here. First one is the process window, where we define our process. Second is the object catalog window, where we input the input parameters required for the process. And third one is the GUI. Okay. So for any welding simulation, okay, we need only 5 parameters. Only 5 parameters. So first one is the geometries. So you can import the CAD geometries. You can import the mesh.
I think there is some problem with Mr. Sandip. Hello, Mr. Sandip. Are you still there?
Sandeep, are you there? Give me a minute, let me call this number.
Okay. All right. Okay. Maybe we wait for a while to get connection with Mr. Sandip. Thanks. Yes.
Barangkali silakan kalau ada pertanyaan, Pak. Nanti Pak Armansyah yang akan translate barangkali.
Boleh.
Trinitor atau ke Sandip.
Oke, boleh. Mungkin untuk dari sesi emisi software Singapura, apakah dari pihak Entres mungkin akan ada juga tambahan presentasi atau informasi mungkin Pak Didi?
Oh, saat ini tidak, Pak, gitu ya. Cuma saya barangkali akan menawarkan, kan tadi presentasi pertama dari Mr. Trinitor itu General MSc Software. Barangkali ada interest untuk event hari ini kan stressingnya di SimFact Welding. Silahkan kalau ada interest lain, misalkan untuk di multibody dynamics tadi, untuk mechatronics, robotics, atau topik lain, misalkan akustik kah, gitu ya. Silakan sampaikan ke saya, nanti saya akan arrange untuk spesialisnya yang akan mempresentasikan kembali topik-topik yang diminta.
Baik, Pak Didi. Sebetulnya menarik sekali ya informasi tentang kemampuan software simulasi SIMUFACT juga emisi software dalam aplikasi industri atau manufaktur. Saya juga tadi melihat ada couple proses atau proses series dari tahapan-tahapan proses manufaktur, baik dia welding, stamping, bending, ya. Ternyata bisa disatukan menjadi satu sequence dari proses simulasi tersebut.
Ya, dan lebih utama itu ternyata itu memberikan efek yang cukup signifikan berbeda, Pak. Ya, antara kita simulasi satu persatu saja ataupun kita simulasi secara serial tadi, proses serial atau chain proses. Ternyata hasilnya jauh lebih akurat kalau kita satu proses disimulasikannya.
Betul, betul. Nah, ini yang memang belum banyak ditangkap sebetulnya, Pak, dari kita, baik dari peneliti atau akademisi, untuk menangkap ternyata ada fenomena-fenomena yang yang luput dari perhatian kita, khususnya mengenai distorsi ya. Ternyata proses tadi ya, serial proses tadi ternyata menghasilkan distorsi yang cukup tinggi apabila dilakukan dengan satu persatu ya. Saya bisa melihat di sini bahwa emisi dan SIMUFACT mencoba untuk mengeliminasi distorsi tadi ya dengan menggunakan series couple proses ya. Nah, sampai perbedaannya itu jauh ya, bisa sampai milimeter ya, ininya distorsinya. Nah, dari sekian banyak proses manufaktur, kalau kami di UPN, selain di bidang teknik mesin, kita juga ada teknik elektro, kemudian teknik perkapalan juga ada. Tentu saja banyak bermain desain ya, kemudian welding juga sudah ada, proses manufaktur. Kemudian kita juga ada teknik industri, ya. Dan ke depan kita akan membuat satu program studi magister untuk energi. Nah, saya pikir akan banyak nih hal yang bisa diaplikasikan ya, atau disimulasikan proses-proses manufaktur yang lazim terjadi di dunia industri nih, Pak. Khususnya di additive manufacturing ya, mungkin bisa kalau ada sedikit demo ya untuk additive manufacturing, khususnya powder ya, 3D printing, itu bisa juga jadi informasi kita nih, Pak. Karena hal ini masih belum banyak ya, khususnya di Indonesia, untuk simulasi additive manufacturing. Kemudian magnetik mungkin juga, Pak, kalau boleh saya tambahkan untuk magnet, karena kita juga ada di bidang energi dan elektronik ya, elektronika mungkin juga akan jadi satu perhatian buat kami. Apakah ada kemungkinan simulasikan dari sisi energi magnet ya, khususnya untuk generator magnet ya, atau hal-hal yang berhubungan dengan magnet. Itu mungkin tambahan dari saya. Barangkali ada dari pihak lain ya, silahkan, boleh ada yang ingin ditanyakan untuk bisa memanfaatkan sesi pertanyaan ini nih.
Dari Bapak Damora, silakan Pak, ada komen atau?
Iya,
Ya,
silakan Pak Damora.
ya, terima kasih Pak Arman, Pak Didi. Kalau ini apa sih Mufak ya khususnya ya. Karena kebetulan saya di bidang apa KE ya, konversi energi. Jadi ada mata kuliah tertentu seperti aplikasi CFD, computational fluid dynamic juga sepertinya bisa menggunakan ini ya software tersebut. Tadi yang yang menarik juga ada masalah akustik. Ini proses perambatan suaranya itu bisa juga mensimulasikan, apakah bisa mensimulasikan rambatan suaranya itu melalui media tertentu, misalnya benda solid, benda padat, atau media yang dilaluinya itu berupa fluida, cairan. Misalnya bagaimana kita bisa mendengar, katakanlah ikan mengeluarkan gelombang di dasar laut atau di dalam laut ketika berkomunikasi dengan jenis yang lain, ya proses rambatannya itu apakah bisa juga disimulasikan. Kita bisa melihat distribusi sebaran dari suara yang merambat melalui media tertentu seperti misalnya fluida cair atau fluida gas.
Iya, menarik.
Baik Pak Damora, kita mungkin arrange session berikutnya khusus topik untuk CFD dan akustik. Bagaimana Pak?
Ya, bisa Pak, boleh Pak.
Baik.
Silakan Pak, silakan.
Baik. Nanti kita arrange waktunya dengan spesialisnya tersendiri. Nah, tapi tentang additive manufacturing, barangkali setelah topik welding ini, Sandip bisa mempresentasikan additive manufacturing sebagai barangkali overview sebelum kita bisa nanti detail membahasnya ya Pak. Sandip, are you ready?
I have joined.
Yeah.
Very sorry very sorry that I got disconnected.
Yeah. There is also request from Pak Armansyah at the end of your presentations. You can edit the topic of introduction or overview of the additive manufacturing. Is it okay, Sandip?
Sorry, I didn't get you, Pak. What is the request?
Additive manufacturing.
Just overview, just introduction to us right this morning.
Yeah.
Is it possible?
So yeah, how much time they have? They have another 30 minutes.
We have still enough time. Yeah, we still have 1 hour 32 minutes until 12 p.m. 12 o'clock.
Yeah. So Sandeep, are you comfort to take additive, or I should bring Santosh and check Santosh is available?
Just let me check. Okay.
No, I will check. You continue this one. You take maybe next 30 minutes, and then
Okay.
if it's not available, I will join back. And I have 30 minutes meeting, so 11:30 to 12, I will just drop out and I will join back at 12 p.m.
Okay.
So by 12 to 12:30, I will take the additive presentation. If Santosh is not available,
You will make the presentation.
either I will do or I will ask Santosh to do. But I will
Okay.
join back at 12 p.m. I mean, in the next 30 minutes.
Maybe I can give you the small introduction if it is.
Yeah, correct, sir. So you continue first welding first, and let's see how it goes.
Okay. Sure.
That's fine.
Okay, so I will share my screen.
Yeah, sure. Please, Mr. Sandip.
Okay, great. So minimize this one. So, okay, I'm not sure when I got disconnected. So I was explaining that. Okay, so first I explained this one, in which I have to select the process type, which process type I have, and we have different components over here. The parameters. First one is the component, The bearings is part of the fixture. Then there's the boundary conditions, the clampings, and the local joint is used for the, tack weld or something. And then the robot is for either for robots or the manual welding. Okay. So we have this kind of, we need to fit those information. When I say, okay, it has opened the 3 GUIs. The first one is the process window where I can define my process. Second is the object catalog window where we input the input parameters required for the process setup. So for any welding simulation, the 5 parameters are very important. Okay. The first one is the geometry. Second is the material, the temperature, the trajectories, basically the welding sequence. And the last one is the welding parameters, basically the heat source. Okay. So those parameters I will explain. As a geometry, you can import the mesh file. You can import all the CAD files. So all types of CAD formats, we can import the IGS, CATIA, Unigraphics, Parasolid, all types of we can import. Okay. We can also create the basic shapes. So I have imported the 2 parts over here. Okay. And I can just drag and drop it like this. Like this. Just select it and drag and drop it to this one. Drag in and drag it. So it is very, very easy to use software. Okay. And also you can see that we don't need the mesh equivalence. Basically, mesh equivalence means node to node connectivity between the 2 components. Okay. Now we'll come to the second parameter out of 5 is the material. So in material, you can create your own material, or we can import from the other sources like the JMAT Pro, which can give you the, the material curves. Also, we have a huge library. So I will say material library. So we have 774 materials, out of which 64 are for the welding applications. Okay. So we have a different materials right from the aluminum, steel, the Inconel, titanium, all those material things we can cover it in our SimFact library. So I will take one of them just for the demo purpose and say okay, and I will show the material properties. So I double click those material properties. So for any welding simulation, 3 properties are main important: thermal, mechanical, and the flow curves. So all those thermal properties like the thermal conductivity, specific heat capacity, density, all properties are temperature dependent, because during the welding operation, the temperature rises a lot. And with that, those properties also changes. Okay. So that is why we have this with respect to the temperature. Similarly, the mechanical properties like Young's modulus, thermal expansion coefficients are changing with respect to temperature. So this graph showcases that stress versus temperature, and it changes with that. And we have the flow curves. Okay, so this is nothing but the stress versus strain graph. Okay, and with respect to different temperatures. Okay, with respect to different temperatures, we have this kind of graphs. Okay, so these properties are very important, and all are temperature dependent. So we'll get the very, very accurate results. The third parameter is the temperature. So basically the initial temperature of the components we need to define. Okay, and also we can define the heat transfer coefficients. Okay. And the next 4th parameter is the trajectory, where we can define our weld line basically. So just simply like this. So what I need to do, I need to select the starting point of the weld and end point of the weld. So like this, it can connect all those dots over here. So this is my starting point of the weld and this is my end point of the weld. So it automatically select in between nodes and say okay. So I will assign this material to everyone. So I just drag it to the process and it will automatically assign to everyone. So you can define the different material for each components. Okay. Then I can define the trajectories to the robot. Okay. Later on, we'll see what are those arrows and this means, and come to the last part from the object catalog window is the heat source. So I just right click and then see heat source. Here we define our, the welding parameters first. This is the torch velocity. I can select the unit as per my requirement. So I give it some random values of the torch velocity. This velocity is nothing but the torch velocity, welding torch. And we have different types of heat source, heat mode, indirect power and the direct power. In the indirect power, we mention the values of current and voltage. And in the direct power, we mention the wattage value. Okay. Mostly this direct power is used for the laser welding application. Okay. So for demo purpose, I'm choosing this indirect power. Let's say current as 120, voltage as 30 volts. Okay. Based on these parameters, it calculates automatically the heat energy that we are going to put inside into the component. Okay. And with the efficiency, we can calculate the total energy, the net energy we are putting. Okay. Then there is a heat source model. Okay. So this is the based on the Goldex double ellipsoid model. Okay. So this is nothing but showcases that this is the heat volume. Okay. And there are different types, the conventional and the laser welding applications. So we need to define the heat volume based on the Goldex double ellipsoid model. So what we need to do, we just click on this I button over here. And there are two ways to forward those information. One is with the help of micrograph. If you don't have the micrograph, we have the equations over here. So we just put the value of the A. So this is my one component, this is second component, and you just calculate the A value and put it over in these equations and put those values over here. So I will right now put my values over here. Okay, so I can put those values. I can put the secondary heat source information. And also we have a facility to provide the secondary heat source. Okay, so for example, you have the two types of welding we are going to add. Like for example, the one is the laser welding, one is the arc welding, and you're doing concurrently or the tandem welding. So we can define the secondary heat source as well. Okay, in that it is mostly used in the academics. Okay, and I say, okay. So I calculate the heat source, and then at that heat source, I can apply it to the trajectory. Okay. So I have completed my 5 parameters. Now I will come to the process tree window. Okay. So first of all, I will create some fixture for this one. So I can just directly go to the bearing. I will create one simple base plate for this one. So I will just say create a cuboid. I need to select the location. I just click it, drag it, hold it, and just release the button. So I can just create this kind of base plate. I can change the sizes of it and say, okay. So I created one base plate on top of this. This wheel is resting. Okay. Now I will create the 2 clamps for this component. So I will just again similar process. I will generate some clamp on the top of the location over here, like this. Also one more clamp, like this. So in the clamp properties, what we can feed the information is that activation time. So for example, after some time you want to remove those clamps, we can specify that time also. Let's say, for example, after 10 seconds, I want to remove those. I can feed that information. Also, I can put the information of the clamp force. So let's say 0.3 kilonewton force I'm applying on this clamp. And with this calculator button, it will automatically select the direction, the force direction. And you can see that for this clamp, this is the clamping force direction. Similarly, for the robot, I'm mentioning the 10 seconds. So after some time, 10 seconds, I'm going to remove those clamps. Say 0.3. Say okay. Okay, so from the geometry point of view, I have finished this one. Now I will come to the robot settings. Okay, so you can see that in the welding sequence, it automatically calculates the total length of that weld. Okay, how much time is required for that particular weld, you can see over here. Also, for example, just for example, so this is my first weld. Okay, if I want to start the second weld from, let's say, for example, from here to here, somewhere like this. Okay, so we can give that information. So let's say, so there is a weld sequence over here. When I finish my first weld, the weld torch has to move from end point of this weld to the next point, the starting point of the weld 2. Okay, so there is a travel time is there, and there is no heat energy we are adding into the components. So that time also we can specify over here. Let's say, for example, 2 seconds, we can feed that information over here. Okay, then in the trajectories, what we define is the torch angle. Okay, so basically when I say orientation, as soon as I click on the orientation, you can see this is a schematic view where the pink arrow showcases this is my torch angle. Also in the GUI, you can see these arrows. These are nothing but the torch angle. And I can change that torch angle also, rotation angle. Let's say, for example, I want to move it by 20 degree. So I can change that torch angle by 20 degree. Okay, so like this, I can define it the torch angle also. Minus 20, so it will move in the above direction. So plus minus, it can do it. And the next parameter is the weld bead generation. So we are creating the filler. Let's say generate weld filler. So by default, we have the two types, triangle and the quadrangle type of filler we can create. And for the triangle, we need to feed those information. So when I hover my mouse over there on those parameters, it will show that what is mean by A, what is mean by B, what is mean by Z1 and Z2 in the schematic view over here. Okay, so what I need to do, I just need to put the information about the Z1 and Z2. That's it, and it will automatically calculate the A value. And rest thing, you can just keep it as it is and say preview. So it has created that geometry by itself, okay, and meshed it itself, okay. So I can select the different types of the mesh qualities, coarse, medium, and the fine, and say preview. So I can see that the change in the mesh quality, okay. And again, I come to the trajectory and open project on the surface and say okay. Okay. I can cross check whether I have defined correct. Please just click on this animation. So you can see that my heat source is moving. So this is how it looks like. Okay. And then I come to the last thing, that is the process parameter, where I can define the types. So if we can run the two types of simulation, thermal simulation and the thermomechanical solution. Okay, in the thermal solution, we can just simply see only the temperature related results. And in the thermomechanical, we see the results like temperature plus structural, basically the distortion stresses. So first, thermal solution is needed only when you are going to calibrate your heat source. Calibrate heat source means whether the given heat source is correct or not. Okay, whether it is creating proper weld pool or not, we can verify that. Okay, once we verify that, we can run the thermomechanical solution to find out distortion and stresses. Also, we have three different types of precision modes: normal mode, precision mode, and the fast mode. Okay, the fast mode will give you results within very short time, but the accuracy will be less compared to normal and precision mode. So normally we use normal mode. Okay, then the parallelization is provided to run the simulation faster. This is the time control. So this automatically takes it from the robot. So I can define the 300 total seconds time, out of which 11 seconds will be used for the welding operation and the rest will be used for the cooling operation. Say for example, when you finish this welding, all the welding operations, and then you remove it from the machine or from the, and you keep it on the ground or the in the clamp condition to cool it down. Okay, so that time also we can add it, which is very influencing on the distortion and the stresses. Also the local refinement, we can use it, adaptive meshing basically. So as the weld goes on, it will automatically mesh the nearest area. Okay, and say, okay. Now I will just check the model, whether there are any errors are there in the model or not. It can showcase you over here. So it says that model check successful. Say for example, I will remove one of the component from the material. For example, I'll just say remove and do the model check. So it has given me one error. So it says that no material has been assigned to the following component, that is the plate. So I can just again assign that material to this one. So no more. Now I can run the simulation. So I already run this simulation. Now I will show the results for you. Okay. What different types of results we can see it. Okay. So this is my result window. And these are the different types of results I can see. So in the standard results, we can see temperature, peak temperature, total displacement, stresses. Okay. I can see all the temperature related results, heat flux, temperature gradient, all types of displacement in every direction, all types of strains, all types of stresses I can see, the flow stress, equivalent stress, normal stress. In the phase transformation, I can see the major phase index, volume, the percentage of the different phases, perlite, benite, ferrite, hardness, full stress, cooling rates, I can see the mass portion of the different components. Okay. So like this, lot of results are there. Mostly people needed this temperature, peak temperature, displacement, and the equivalent stress result. Okay. So when I switch on my animation, so you can see that welding operation is happening. I will show the boundary condition also. So after some time, this clamp also get removed. I can see the welding operation is happening over here. How is the effect in the heat affected zone? I can see. So you can see that after some time this got released. I can see the peak temperature results. And these are the different temperature zones I can see during that welding operation, how it occurred. So this is very important in the academics to know the different zones or temperature zones over here. I can see the equivalent stresses. Okay. I can check the cross section. Like this, I can see over here. I can just do it like this. I can multiply as many as want the cross section. Well, also with the query button, I can see the different result at any point at any cross section. I can see those results. Okay. Also very important results. Suppose, for example, you might remember that 300 seconds time we have defined. And I want to see that during that 300 seconds time, how is it is affecting at this, how it is result changing at this particular node, for example. So I can see that graph, that basically the time history plot. So at this particular node, so it is tracking those things. So you can see that for the 300 second time, how is the temperature changing at that particular node? I can see it using this graph. I can choose as many points I want and see the results. Okay. Apart from temperature, I can see the stresses, the displacement, and you can see all those results in the graphic format. Okay. So next important result is that the weld pool. Okay. So on the right hand side, you can see one green plane over here. Okay. That is my cutting plane, and that shows the cut section on the left hand side. And when I switch on the animation, okay, this cutting plane is moving, and on the left hand side I can see one red zone over here. This red zone is nothing but the molten area. Okay, so this much area will get melted during the welding operation, and I can measure those welding things, the major things. Okay, so with the given heat input, whether it is correct or not, I can see it clearly in those example. So if the heat source is very high, this red zone will cross the plates, which is not desirable. So we should have the optimum one. Okay, so this is the important results. Another example we can, another important result is we can do the shape comparison. So we can just know that how much it has deviated from the original position. Okay, also if you have a 3D scanner, we can scan those final components and bring it over here and compare it here. So you can see that surface deviation happening. How is the surface deviation is happening from the original position? So you can see that when there is one small transparent part is there. So that is my original position. And after welding operation, this is how it has deviated from the original position. So we can see that clearly over here. Okay. So this is the important of the shape comparison. So the UNV export is when needed when you want to do the structural analysis or the fatigue analysis. So from here you can select the geometries you want to export, the increment, at what increment you want to export the results, what type of result you want to export, and then it will create one UNV file which can be used in the further analysis. Okay, and we have a huge help documents which is very easy to use. Okay, so when I open that demos and examples, we have a tutorials, okay, which has step-by-step procedure how to do the particular welding, that particular simulation. So it will show that step-by-step procedure, training material is there. Okay, for each type of process. Okay, we have different examples for each process. For example, the robots, multi-layer welding, the circular plate, the wave on the plate. For laser welding, we have gear shaft welding, this solid shell, laser metal deposition, the brazing operation, the spot welding. Then we have, for the example, for the DED operation. Okay, so like this, we have a huge help documents and very easy to use software. Okay, so this is from my side. So please let me know if you have any questions. Okay, so yes.
Okay, thank you very much, Mr. Sandip.
Thank you.
Now I would like to open a session for Q&A. So sekarang kita sudah selesai mendengarkan sesi presentasi dari Mr. Sandip. Bagi yang ingin bertanya, saya persilahkan.
Question from chat from Pak Damora.
Yes.
Sandip, what the minimum computer specifications for the software, particularly
Yes.
the simple welding?
Okay, it needs a simple just simple workstation, okay, which has let's say, for example, 32 GB RAM or the 64 GB RAM we can have. And normally the lot of computers come up with the 8 cores, so we need that 8 cores. Okay, so only very simple hardware is needed for our software. So 8 cores and 64 GB RAM works really well. That's one.
The processor i7 is sufficient?
Yeah, sufficient. It is sufficient. Yes.
Okay, i7, yeah.
Send you the document also if you want. What is the basic thing?
Yes.
Required?
Yes, it's very good if you can share the information regarding to the computer specification for doing
Sure.
for using software. Yes.
Okay, sure. So right now, computer
yeah.
I'm using is like It's just 64 GB, 64 bit, 64 GB RAM, 8 cores. So it's a basic, simple laptop I have, and it works really well in that way. But I will send you the document. Okay.
Oke. Mungkin Pak Damora ada yang mau ditanyakan lagi, Pak? Silakan, Pak. Oke. Question from Mr. Damora. Can Simufec boundary condition using UDF, user-defined function, for simulation that have unique boundary condition?
Yes, we can define those unique boundary, user-defined functions. We can define it. Yes, definitely. Yes.
Okay. Okay, that's. I think we have enough information regarding to the welding simulation. Yes. Is there any demo beside the welding that you can share with us today?
So if we have some time, I'm not sure, I can just give you the information about the operation if you are interested.
I see. Okay, good.
I need to check with the Trinitor also what is his plan for the additive.
Yes.
So,
Later at 11 will be present about the additive manufacturing, Sandeep.
so how much time I have now?
We still have time more than 1 hour until 12 o'clock Jakarta time.
Okay. Okay, so I don't have that much material for that 1 hour, but I will cover this very interesting topic, which is more in the academics and the research institute and the right now the industry also. So it is a kind of additive manufacturing process. Okay, so this is the direct energy deposition, which is mainly used for the generate parts, clad parts, and the repairing parts. Okay, so this is kind of additive manufacturing process we have. So this I will skip it. So this is the basic principle of the powder-based DED process. Okay, so this is my base plate. On top of it, I am adding the layer by layer. Okay, it's a kind of additive manufacturing process again. So this is the powder I'm adding, and I'm also having the laser source. This laser source is melting that powder and depositing, the powder on top of each other. Okay, so this is a typical DED process happens, and this is a typical seam geometries we can see. This is all the micrographs. Okay, and this is the what objectives we can have it, what is needed. So from the academics or the institutes, that fast prediction of the distortion, identification of the local heating areas, hotspots, includes hybrid approach for the repairing parts. Okay, so what it does basically, you can see there is the damages happen to the airfoil. Okay, so what does this DED does? It adds those, we are repairing those damages. Okay, by adding the material, by depositing the material. Okay, so like this, then you will get the perfect again the shape, because sometimes what happens that we cannot create this airfoil from the scratch. Okay, then it will involve a lot of cost in that one because of the material cost. Okay, so this is the normal workflow happens. Okay, this is the CAD models, this is the DED path planning. Okay, and it provides the G code, and this is how it looks like on the actual one. So this is the current process, And then what we do, instead of doing on the shop floor setup, we provide that G code to our software and do the virtual testing. And you can see that how it is layer by layer adding into the component. Okay. And then again, check it. So these are the institutes we have, tie up with Research Institute, the Fraunhofer, University of Dresden, the Bionic BAE Systems, and this is the commercial and the research partners. Those research, we included it in our software. Okay. And this is what how it works, that the heat source, basically the real laser intensity looks like this. Okay. On actual, this is how it looks like. Then we idealize this laser intensity. So we create, average it out properly, and that heat energy, that heat source, we are going to use it. Okay. So this is just to show that different examples. So this is the having the example for the validation of the heat source with the experimental one. So in the experimental one, you can see this micrograph over here. So this is shows that how much area has been melted. Okay. And in the simulation also, we can see that. And the graph showcases that the comparison of the shop floor result versus simulation result. So this thermo elements, nothing but, so we have a thermocouples to measure the temperature at different locations, and that measured, we can compare it over here. So you can see that very good correlation between simulation and the experimental one. So you can see over here, this is the example. Okay, the small plate and where the deposition is happening over here. And these are the different points where the temperatures will be get calculated. And there are different stages in that total process, like the DD operation, then the cooling operation. So at different stages, we can see the comparison, and we have the correct geometries. Also, the defects like the delamination or these things, we can predict it using the high stress or the plastic strain. Okay. And this is the temperature versus simulation comparison. So you can see the different peaks. So this showcases that during the welding operation, the temperature rises a lot. And then in the cooling, the temperature, comes down. Again, something like this happens. So this is the layer wise information. So first layer, second layer, third layer, fourth layer, fifth layer, like this, these things are there. So this is an example of the 30 layer, the metal deposition, and this is the comparison of simulation versus experimental. So this is a distortion comparison for that earlier study. So we can study that study on a thin part with a varying stiffness. So this is a convex side and concave side. So it has a varying thickness over here. Okay. And this is how it looks like on the actual one. So DD is a part of the additive manufacturing process only. And these are again the simulation and the experimental result comparison, and that standard deviation, we can see it over here. So the blue one is with the simulation, the black one is the experimental result. So this result is done by the Fraunhofer Institute. Okay. And also you can see that the stress deformation happening after wire cutting operation. So we can do that, and this is how it looks like before EDM, the wire cutting process, and this is how it looks like after the EDM process. So we can see the different results at different stages. And this is how it looks like with the scan geometry. So this is the simulation method. So we provide the CAD format as was shown in the demo, and we got the distortion values. And this is how the actual one. So we printed the part, then with the help of 3D scanner, we scan those components and get the CAD geometry out of it. And we are comparing the simulation versus that shop floor result. Okay, we can do that same comparison. Also different material types we can use, that powder, cold wire, the hot wire. Okay, different things we can use. And this is the turbine blade. We can see that layer by layer addition is there. So there is 30 layers are there, and we can see the distortion results. So we can see that here it is a 0.7 temperature deformation distance. We can see it over here. So currently we have implemented a lot in that one. So currently we import the G code, or the manually we can define it. And these are the yellows you see are nothing but the the torch, basically the trajectories, okay, the tool path basically. And this is how it looks like on the software. So we use the direct energy deposition. We import the G code, which has the information about the weld lines or the DD lines. You can see that. Then now we are creating the one base plate over here. Okay, then we are meshing it, the component, that base plate. Then we are going to add the deposition material. Okay, so we are putting that information over here. Okay, so it will cover the area of the tool path. We need to confirm that. Okay, and once we clear that, okay, so it is covering that part. So then now we are assigning the heat source, now creating the boundary conditions, and now we are going to start the simulation. Okay, so now you can see that this much thickness will be the layer deposition will happen. Now we are running the simulation, start analysis. Now you can see the results. So like this, it is layer by layer addition. So over here you can see clearly. So you can see this temperature results in the animation over this one. And these are different G codes. We are going to implement the different sections. Okay. And this is for the circular parts. You can see this is the actual one, the substrate here. And this animation showcaser, we can on the circular tube also we can do that this thing. Also we can see for that example how it is changing the shape also, and it is depositing layer by layer. So from small parts till the big parts, we can do the simulation. So this is the WAM process. So this is a kind of a wire arc additive manufacturing process. So this is the weld pass over here, and this is how it looks like the deposited geometry, and this is how it does actually looks like. Okay, over here. So there are some 63 layers are there and there are 530 meters weld line is there. So almost a half a kilometer we have. And so this is the simulation time requires, but recently we have added one more approach in our software. So this is little old one, but we have added one more capability. So earlier it was required 5 hours. Now it will finish within half hour. So just 30 minutes, we can finish this kind of simulation with a good accuracy and everything. And you can see this is how a metal deposition happens. Okay, so this is the last slide of that one, and so that's it. DED side. Okay, so this is a additive manufacturing, but comes under welding operation, and which is for the academics, it is very it is now getting famous in that. So that's it from my side today. So I believe I will still have some half an hour, right?
Yes, sure.
30 minutes. So I can see that we can take a break of 30 minutes, and then my colleague will start on the additive manufacturing process.
Okay. Very interesting information. By the way, do you have also any case study in fluid dynamic simulation, for example?
In what areas?
Aerodynamic, fluid dynamic, for example.
Kita arrange berikutnya Pak, karena Pak Sandeep spesialis in the welding.
In welding ya. Oh, okay.
Ya,
Okay.
Ya.
Fine.
Jadi dari tadi Pak Damora, nanti saya arrange untuk yang CFD dan akustik. Lalu untuk topik lain kita arrange juga dengan spesifik spesialisnya, Pak.
Boleh Pak. Wah, senang sekali.
Baik, silakan. Baik, berikutnya barangkali Trinitor, Pak, sekarang udah siap untuk introduksi tentang additive manufacturing.
Iya. Silakan, Pak.
Trinitor? Sambil menunggu Trinitor, saya ingin tambahkan, silakan untuk seluruh sivitas akademika UPN-VJ bila ada nanti pertanyaan ataupun inquiry, barangkali silakan sampaikan ke Pak Armansyah, nanti Pak Armansyah komunikasi dengan kami di MTrust Indonesia.
Iya, siap. Baik.
Terima kasih
Siapapun.
sebelumnya.
Ya, silakan, Pak.
Baik, Pak Damora, barangkali kapan kira-kira kita setting session khusus untuk CFD dan akustik, Pak? Kira-kira nanti saya propose ke MSC-nya.
Kalau di Jumat depan gimana Pak, bisa di hari-hari Jumat minggu depan?
Baik, Jumat itu sebelum Jumatan atau setelah Jumat? Pagi?
Pagi aja ya hari.
Siang?
Pagi, jam seperti jam sekarang, jam 9.
Baik. Nanti saya sampaikan ke MSC-nya.
Jadi akan ada sesi lanjutan ya Pak untuk CFD dan akustik di minggu depan, insya Allah hari Jumat pagi ya Pak ya. Allah.
Topiknya tepat Pak Damara, CFD akustik? Ada yang lain maksud saya, concern dari Pak Damara?
Yang akustik juga menarik karena media perambatannya kan menggunakan ini media gas menggunakan fluida ya, fluid dynamic. Saya sering melakukan simulasi di CFD itu kan menggunakan flow aliran fluida cair atau fluida gas. Tapi kalau di bagian yang akustik ini saya belum begitu banyak mengeksplor dari berbagai macam software ya. Memang kalau di UPN itu kita sudah punya salah satu software ANSYS Fluent, juga bisa digunakan untuk simulasi CFD. Tapi masih banyak yang yang belum tereksplor gitu mengenai fluid dynamic, karena di bagian ini fluida tersebut misalkan aliran suara, ternyata suara itu bisa mempengaruhi pola aliran yang terjadi di aliran fluida. Jadi kalau misalnya ketika frekuensi suara itu ditinggikan atau high frekuensi, maka alirannya itu yang awalnya aliran laminar flow bisa berubah menjadi turbulent flow. Nah, dan itu juga yang cukup menarik kalau dari saya untuk melihat fenomena kenapa bisa frekuensi suara bisa memberikan efek terhadap pola aliran selain dari aliran fluida itu dipengaruhi oleh berbagai macam hal, misalnya untuk kekasaran permukaan atau dimensi dari ukuran saluran dan lain sebagainya.
Ya, menarik Pak Damora. Nanti kami sampaikan. Bila untuk welding ini modul kami namakan Simufek, nanti untuk CFD dan akustik itu akan modul kami itu bernama Cradle dan Uptrend.
Cradle dan Uptrend daripada modul emisi software ya
emisi
Pak ya?
software, benar Pak. Ya. Nah, ini juga ada pertanyaan di chat tentang gelombang elektromagnetik. Jadi kita range session berikutnya lagi Pak Armansyah tentang tadi pertanyaan Pak Armansyah magnetik dan termasuk juga elektromagnetik ini ya Pak.
Elektromagnetik, iya. Salah satu menarik juga Pak buat kita, khususnya di Departemen Elektronik, ya, elektro dan elektronik.
Baik, baik. Silakan Pak Armansyah, Trinitor sudah ready saya kira.
Yeah. So electromagnetic, we can address through Mark. Mark has electromagnetic, piezoelectric, MEMS, so those kind of analysis simulation types. So maybe Park Didi can send you details about that. Hello.
Yeah, Trini.
Yeah. So electromagnetic and those things you can send them later, Park, because it's in the Mark, piezoelectric, MEMS, electromagnetic, electrokinetic, all those things are there.
Yeah. Later I will communicate with Pak Armansyah to prepare these topics.
Yeah, okay. And also CFD and acoustic also we can arrange a separate meeting.
Yeah.
Just give me a minute. Let me share my screen.
Yeah, sure. Please.
Yes, I'll share my screen. Are you able to see my screen now?
Yes, now it's okay.
Yeah, so this is basically an AM slide. Of course, I understand Sandeep has done, he covered already. He covered already the, the DED perspective. So, but so this agenda, it has powder, laser powder bed fission and sintering. And just 1 minute, I will just follow. Okay. Ask my colleagues to join. 1 minute. Yeah, so sintering, and sintering is basically binder jetting, and the DED is another welding technology, but we use it in additive, and then machining, and then plastics, polymer, and topology optimization. Now, can I know what kind of technology you are looking on keen on? Is it powder bed fission or binder jetting or DED welding or machining or plastics, polymer? What kind of printer you have right now?
Right now we have plastic and polymer.
The plastics and polymers. So you have a Stratasys or something, is it?
Yeah. In the future, we plan to have also for powder and metal.
Okay. Yeah. Fine. Anyway, I will just, it's a long presentation, but I don't know how much time I will have, but I will try to cover as much as possible. And I have asked my colleague also to, join and see if we can show some, powder bed fusion, some demo, software demo.
Okay.
So this is again introduction about Hexagon. Like I mentioned, Hexagon is into agriculture, geospatial, geosystem, mining, and everything. But we belongs to DNE, the design and engineering team. That is where our marks, MoveFact, all the solution, Cradle, acoustic, everything we talk about. Now these all are couple of powder bed printed parts actually. The components of applications. And the quality of AM parts, it depends on mechanical properties, process, cost, trial and error. For example, when you print, some deviation will be there, some distortion will be there. You see the right side, there are some cracks are coming. So these all are general issues you will face when you go for a metal printing. Now the solutions what we have is MoveFact. So we can bring the CAD file and we can print it in a computer, so that you don't waste your time and your cost and money in actual printing or trial and error method. And the support structure generation, and for example the orientation, whether you wanted to print the vertical, horizontal, so all those things you can do virtually here. And then you can reduce the time as well as the cost and money, everything. And then finally, you can go for an actual printing. And we have collaboration with Materialize, which is a Magix software, or we can have Additive CAD. That this tool will support support structure. Of course, we have our own support structure generation SmoothFact also. And this is just to show you how, the same component, when we print horizontally, you see the less distortion or less red color areas. But when we print vertically on the first one, you see there is a red color spot which is having deformation out of dimensional area because of the height, the material, and all those things. It plays a very important role. Okay. And this is another example to show you, and just 1 minute. Okay, so this is actually just to show you about the recoater collision risk. You see the red color. See, normally in the printer, what will happen is when you may print like 5 hour, 8 hour, 10 hour, or maybe 2 days. But after some 15 hour, there will be a crash or there will be some failure, and then you need to change the parameter and reprint again. That is waste of time, right? So these kind of situation we will able to find in software itself. And you see the left side, there is a crack is happening, and the right side, the same thing we predicted using simulation. So when you change the design, change some parameter, change the layer, the laser beam and where the voltage and everything, you will able to modify and adjust it so that you can print right at the first time. These all are, the string line prediction. When you print even right side, it's an actual printing. You can see there is a line, string line we call it. And the same thing we are predicting even in simulation also. And then we have another option called compensating the geometry. For example, when you print, it was like, it is out of tolerance. But you can change, or there is a software, there is a button, you can compensate the geometry and it will, come back to its reverse direction. And then, the second iteration, you see the tolerances, went back on, 1 mm to 0.2 mm, and then, the iteration 6 is 0.05 mm. It's very, very highly accurate, when you compare with the first run and the last run. So this is where, you can improve your, your dimensional tolerances. And then hybrid manufacturing, when you print something component on top of it from the base plate. So this is also, especially when a turbine blade kind of application. So we have a hybrid additive manufacturing also. And then we have a tool for cost estimation, and you can see the build timeline hours, then the hourly rate, machine fixed cost, order cost, all those things. You can compute and you can see how much is the cost for the particular product. And then we have optimization tool. It's topology optimization. You just define the fixing area and the loading area and the manufacturer constraint, and it will automatically optimize. And the same thing, you can print it in 3D printing. And this is a couple of example. This is one variable of the same concept. This is another. This is again another. And different orientation. Like for example, is it one part? This is the base plate, and this is the build space. Is it one part or multiple part, and different orientation? So these all are the areas. The parameters you can play around, and you can improve your simulation in order to reduce the cracks or reduce the deformations. And this is support structure optimization. You cannot have more support structure also, but then later you will have some problem of the material wastage, and removal, support structure removal also will be a costing. So you need to be in an optimal way, not over support, and also at the same time not under support also. So that's the way the software will give you an optimization by itself. This is some of the build simulation process. The layer by layer, outer layer by layer, the build thing. We can simulate in the software. Then this is just to show you an automated compensation. So initially in the first simulation, you see the surface deviation is 0.8 mm. But later, when we compensate it with the software, it is 0.02 mm. So you see that the kind of, the improvements or, the deviation or, the performance improvement we are getting. And now when the after once you're okay, then we can send this one back to the printer, print right at the first time. So you won't waste 3-4 trials and errors and those. And this is just to check on the cost base commercial evaluation. So how much it will you will get an estimation calculation per part, how much will be cost. And this is CT scan analysis. So we have something like volume graphics where we can study the internal porosity, the internal volumes, internal cracks, and those things we can study that from the CT scan images. Then sintering, it's again binder jetting basically. So people call binder jetting or sintering. It's a HIB process. And this is also, the part shrinkage, it is very difficult to predict. Again, green part geometry, sintering cycle. So these all are the challenges we face when we do the sintering process or binder jetting. So this is one of the examples to show you a bevel gear, which we have done using printed here. And this is just to show you that. And then yeah, this is just a result overview of grain size basically, in terms of micron level, the grain size predictions, and also the density, because the sintering, the density is one of the important challenge. So the density prediction also we will able to capture using the software output. And this is again a compensated geometry. So you can see here the geometry compensation we achieved less than of 1 millimeter tolerance level, and which we did only with the 3 cycles to achieve this level. And this is DED. I think Sandeep already covered, so I will just skip this DED portion. It's basically a welding one. So this is the workflow we are trying to build of G code. So then we have a machining. So machining is another process simulation, and the pain and gain of the machining things can be milling or drilling or grinding. So the way of the material is the material removal. So in so this is another module. So the solution what we offer is the toolpath generation from our CAM software like EdgeCam or eSpread. This is our tools. Then it will create an APT or the G code. So then it will come to NC Simulink. I mean that's another CNC simulation software. So we will import the trajectories and then we will export 3D volumes. So then the 3D volumes will come to SmoothFact additive, where we will compute the distortion and the build process, 3D print process. Again, that will come back to import the distortion or stock simulation verification again in the NC Simulink CAM software. And this again will come back to the CAM software. It's an iteration. So this is how we will improve the machining simulation the workflow. And this is an I think I would say this is one of our first module or first technology in the market from any of the software companies who offer additive manufacturing, considering this is a machining module as well. So then plastics and polymer, I think you may be having SLS process or FFF or FDM. It's a plastics, polymers and composites. So this is again the results like wattage, crystallinity, counterwrap shapes, support failure. So these all are the the results we will able to get it from a tool called Digimat. So this is again will deal with this process. So the powder bed fusion, the sintering, binder jetting, DED, that is from SmoothFact, that is our metal group, and this Digimat is from our plastics, polymers, and our the composite team. So who build this this technology, SLS and FFF and FDM. Topology optimization, it's another hot topic when it comes to additive, because in additive you will able to build or manufacture whatever the traditional ways are not possible to do basically. So anything here which is very tough to do, like our regular mold and die or any kind of traditional methods, we will able to do that. And the good part about this is if you can see the initial shape is like this, and then the software will do the optimized way in a way like so it is understand the load and support, and then you will able to print it. So this is just to show you an example of, we call it Apex generative design. So we have the generative design tools to make designs very feasible for an AM manufacturing. So it's a lightweighting. Lightweighting is another one of the important key point: efficiency, time to market, and cost. And many of our projects, we are able to reduce 50% cost. I mean, weight reduction, 63%. Then reducing this fixation, all those things, we were able to come up with, considering all these facts. We are coming up with the best designs for additive. So this is a CAD to CAD workflow. So this is again Apex generative design, and this is just to show you a screen capture. Whatever the metal printer you buy, it can be. So this is for SLM, but you can see here you have SLM, EOS, concept laser, Renshaw. So all these material database, the library is here inside. So we can just pull and choose whatever the machine you buy, and we can just straight away click, and all the data are there, and you can run it. So this is about just overview of our additive solution. And Santosh, are you there online?
Yeah,
Santosh, yeah, Santosh, can you
Yeah,
just show them one simple example of a tool of the SmoothFact powder bed fusion?
okay. So maybe a couple of published case study.
Yeah, maybe our one case study or something you can show. Yeah, but
Okay, done. I do that.
any question, by the way, Professor?
No. So far, okay. So far, fine. Thank
Okay,
you.
Yeah, okay. Any question, Dr. Damora? Yes, Santosh, we can see the screen. Yeah.
Okay, yeah, I hope you can see. Okay, so to give a quick introduction. So when I say additive manufacturing, so we are not only focusing on powder bed fusion. So as Pini already explained, we have solution for powder bed fusion with SLM technology, metal binder jetting, DED. Then when it comes to polymer and plastic, so we have Digimat software where we can simulate FFF, FDM, and SLS process.
Hello.
Sorry, I forgot. Any questions? Okay. So overall, we want to help the manufacturer to print the part right at first time and eliminate the defect, as well as in the optimization when it comes to printing and cost optimization. So overall idea is reduce the number of trial and error in the workflow. So if you are into the design, so we want to help them to make a design or do the topology optimization, considering manufacturability using different process. So now in design and engineering, we have a tools, before they finalize the design, they can consider what kind of manufacturing process, whether they are going to print this component with polymer, metal, or what kind of process, whether it is metal binder jetting or FFF. Based on that, so we can even do the lightweighting and design optimization. So in fact, the selection of material also available. So this is a kind of integrated workflow we are creating, starting from design, manufacturing, and quality inspection and service life estimation. So I will directly, I will not go through complete presentation. So since Trini has already covered most of the part. So I will directly jump into a couple of case studies which we have done. So this is to show that how industries adapted. So if you ask me what are the industry we support, so you can name any major OEM. So we are working with them. Service Bureau, who does the printing for the OEMs. So we are working with them. Then educational institutes. So we are supporting them. In fact, we have a couple of training courses where we are training the students on design for additive manufacturing part of it, then quality inspection. This is the end-to-end workflow or the platform we provide for any industry or any institute who want to adopt this additive manufacturing technology. So we can start from material to the quality, where we can use a couple of our tool to select which is the best material for the given application. Then start with the design, manufacturing, inspection, then service life. So we cannot really estimate the service life. So I can call it as the product durability, fatigue life. I can call it as fatigue life estimation can be done for the given component. So apart from 3D printing, so we do a lot of post printing operations like heat treatment, hipping operation to improve the density of an 3D printed component, then CT scanning. So we can do the CT scanning if you're into reverse engineering, bring those scan data into CAD platform. So there are a couple of tools where it can directly convert the scan data into the 3D model without much manual intervention, so that we can save a lot of time. Then if we are more into DOA analysis and statistics, so we have a lot of tools where we can help you to reduce the number of trial and error. Again, it might be on the shop floor or it might be on the CAE simulation. So we can use our AI for reduce or optimize the number of runs. So this is an overall picture of how we are working with different industry types with our AM solution. So I will skip this slide. So yeah, again, I will directly jump into. So these are the couple of case studies. So one, we have worked with one of the car maker where we wanted to lightweight. So this is one of the major requirement when it comes to automotive. So they want to do the lightweighting. So this is with the medical healthcare. So recently we have published a case study with replacing a hip socket with a 3D printed implant. So that is quite booming, I can call it as. So we see a lot of 3D printed implants in the healthcare. So where we worked starting from designing an implant, printing of it, then certification, then putting it into the patient. So then lightweighting and optimization, and these are the case study published by Safran and Green Team. There are a lot of case study on using in automotive and aerospace. So this was from Safran. They use their own material. With that, they are able to predict the failure. So I'll quickly run through. So this is one example of how do we
I'll send the video. Yeah, right.
Conventional design with a 3D printed one. So this is a 316L material, which was previously forged, and it had some sheet metal component, and it was joined with rivetings and a lot of overall there were 38 component. We reduced it into 6 by just breaking down it upper bracket and lower bracket, and we could able to print that with a given dimensional accuracy. So in fact, we have tested the 3D printed one. So it will be on the bonnet. So when pedestrian falls on the bonnet, it should lift automatically. So this is also one of the safety criteria. If you look at the high-end car, they have to give 5-star rating for safety. So this is one of the requirement where we could able to replace the conventional with 3D printed component. So in fact, we had a couple of challenges like how do we bring down this distortion below the 0.75 mm. So that was challenge. Then we generated different support structure. Second challenge was how do we address the scalability, like printing multiple component. In fact, we did the nesting. Then we could able to print 6 parts on the same base plate. So that helped us to address the scalability issue. So this with the student race car. So we wanted to have a very light wheel. The lighter the wheel, better the cornering efficiency. So we wanted to lightweight considering the manufacturability. So if you ask me what is the accuracy of simulation, so this is an example. So when it comes to the additive manufacturing, the greater advantage, we can capture each and every parameter in the process. So that simulation results can go above 95% accurate. So this is an example where we start with a technical evaluation as well as commercial evaluation. In technical evaluation, we selected the best design, design for manufacturing and material. So when it comes to commercial evaluation, we did the cost estimation to choose which is a more feasible or economical design, which we can print with lower cost. So then we chosen the one which is qualified from technical and commercial point of view. So these are the case study published by our customers. So this from Saffron. So they made SimoFact as part of process flow before they go for any printing. So they will simulate and understand what are the challenges and modification need to be done. So then only they go for actual simulation, so that they will save a lot of powder. So it is more like a lot of money and time spent on the machine and resources. This with BAE system. So they had issue with the buckling, so where we helped them to design a particular support which helped us to print a component without buckling effect. This with Bosch. So now these are the published case study by our service bureaus, who has used our Apex generative design for optimization and SimoFact additive for printing. So this with the tire industry. So we see rapid growth of adopting additive manufacturing in tire industry. So not to print the tire, so it is to print the mold for a new tire design for a validation process. So instead of printing complete or instead of getting complete mold conventionally manufactured, so they will print 1/4 of the mold for their testing and verification of their new tire design. So this has been quite successful. So where we have printed a component which is in the same pattern of new tire design, and we could able to validate, so that we save a lot of logistics time and cost. So otherwise any new design takes more than 6 to 9 months. So here we could able to do it in 2.5 months. These are the other example of internal cooling channels, how we can do the optimization of internal cooling channels plus 3D printing of it. This is more on medical application. So how implants can be 3D printed. So here challenge is, when I say medical, we use a different grade. That's quite expensive. So we have to print right at first time with the best design or optimized. So these are the other example which we have actually printed and implemented. Yeah, with this I end my presentation. The same time we have continuous support when it comes to training the student, because AM is a new I call it as not familiar as a conventional method. So we do the workshop training until any organization adopt it completely. So with this, these are the couple of customer logo we have. You can name us OEM, Service Bureau, or Educational Institute. So we are working with them for adopting the additive manufacturing technology. At the same time, we publish a lot of e-learning, white paper and case studies to help or to learn more on the latest technology in the market. Okay, so with this, I end my presentation. And any questions? Yeah, if there is no question, I think turning over to you.
Yeah, thank you, Santosh. So do we have some time, extra time, or?
Yes, we still have time.
Santosh,
Please.
can you just, have you opened the software?
Yeah, I have. So
You shown already.
Open in my laptop. So okay, I can share. If you want
Yeah,
to
just
see.
a symbol. I mean, the interface, you can show them a demo. Maybe
Okay.
10 more minutes.
Hope you can see my screen, right?
Yeah, we can see it.
Okay. Okay, so this additive GUI. So we always start with calibration, then running the actual part. Then we go for a optimization. So where software can tell you which is the best support structure. Then we go for a distortion compensation. I will quickly show you what is the advantage of distortion compensation. So when you have a design and you would like to print that part within particular set of distortion values, then you can give the maximum distortion or allowable limit to the software. Then it will run multiple simulation and it will predict with a different set of parameters. It will predict what is the optimized design or compensated design, so which will give you the minimum distortion when we print the part in the actual scenario. So if I do it manually, it takes a lot of time. So I cannot physically print 10 number of variants on my machine. So it is very expensive. So what I do is I will try to use distortion compensation. So to improve the accuracy of the simulation and to match the current condition of machine, I just print 2 small coupon on the machine, so that even though we call it as same material grade, when the same material is supplied by 2 different supplier, the properties might vary, let's say 3 to 5%. To capture that even small variation, we can print a small coupon on the machine. So then we can calibrate it and get those inherent strain value, or I call it as correction value. So then I take that into the actual part printing. For example, I can quickly show the setup. So I go here and I can pick any machine. If you have anything in mind, you can just let me know. I can select that particular machine. So let's go with this. Let me change this to 400. So the moment I change, the respective boundary condition will be loaded automatically. Then I can import the part. So it might be of any CAD native file format. So we support any CAD native file format. So then when it comes to support, either we can import the support or we can create our own support. So it might be of, materialized magics, or it might be of Simufact support. So you can create within the GUI, within the Simufact GUI, no need of any additional a license for this. If you're already using Materialize, so we have option where you can create basic line, block, and point support. Or if you want to use CAD additive support, you can use CAD additive support, which is of contour. So there are many options. Or you can either import it or create support inside the software. Then material selection. So we have already the commercial grades available in the market. So if you have your own material, so you can add those material into library. So I strongly suggest, if you have any new grade, please send it to us, because we are also doing a lot of testing. If it is similar one, so we have already developed material data. We can
Santosh, they are just getting into this 3D printing. They don't have any machine set, for prototype vision. So it's very initial stage.
Okay. Okay. So when it comes to material, so we have the commercial grade available, so you need not really worry. So then we can simulate build, immediate release, and cutting operation. At the same time, if you new one, you are not sure which is a best support structure for the given design, so then we have something called support optimization. So if you activate this, so it will run a couple of simulation, and software will tell you which is a best support structure for the given component. So that is something unique, so that we can save a lot of time or investigating the which is the best support structure. On distortion compensation, as we already seen, you can just define your target value compensation, so that software will tells you what will be the final distortion or distortion control we can achieve with a different set of design. Then we do the voxel and surface meshing. So then we can go for once the simulation is completed, so we can go for a post processing and view the results. I will just move this. This is how we can view the result layer by layer, like how the part is getting printed inside the machine. And we can view different parameters, like what is the peak temperature during printing. Then you can look at stresses developed, how the stresses are getting developed at fixed corners inside the part. Then you can look at if there is any manufacturing risk like recoater collision, if there is a part failure, delamination. Then you can look at relative density in the component, the other heat flux related information, then displacement in each direction, strain, stress. So you can look at all variables which is influencing my part quality. I will just go to the last step. So this is actual printed one. So for example, you have already printed one component and you want to compare this with the original CAD. So we can do the superimposing or shape comparison. In fact, if you have a scanned component and you want to compare with the scanned component plus simulation, so you can import that as a reference geometry, and you can do the shape comparison using a best fit method, so that you will clearly understand what is my initial design and how much it is deviating and which are the location, so that if you want to give further machining allowances on the 3D printed component, you can design those machining allowances over here. So then these results can be exported if you want to do durability analysis or fatigue life analysis. So you can export these results in even file format or any file format which is readable in Nastran, CAE, Fatigue, or any computation tools. You can take this geometry along with the residual stress, so that you will have the more realistic life estimation of an component. So this is a quick overview. So any question on the tool?
Okay.
Yeah, thank you,
Okay.
Santosh.
Okay, thanks.
Thank you very much for all presentation. We still have around 15 minutes till the end, but generally I can see that MEC software or even Simufec can do any simulation in engineering, such as in manufacturing and additive manufacturing, welding, and so on. Perhaps in the next time, we can try to set any discussion in fluid dynamic and acoustic for the next week, inshallah. And perhaps also if we have any question from our side, I will try to connect with Mr. Didi, in as an Amtres in Indonesia, and also if it's fine, also we can try to connect with you in MEC software in Singapore.
Yeah. Sure, Pak. So feel free to, I will drop my email address here. You can,
Yes. Okay. Thank you very
or
much.
you can drop any technical question or
Yeah.
any.
One thing that I can see regarding to the in-plant additive manufacturing, we have also here in the university the medical department, and I think it's also another possibility to do simulation for implant stuff, implant product for medical implant, I think. Perhaps maybe this topic can be joined in the next session with the fluid dynamic and acoustic session. discussion. Maybe I will try to invite in the medical department side in the discussion. Inshallah. Okay, maybe saya coba floorkan bagi yang ingin bertanya. Kita masih ada waktu sekitar 15 menit sebelum habis. Barangkali mungkin ada yang ingin bertanya. Atau dari mahasiswa nih, ada banyak juga mahasiswa yang ikut hadir di sini. Silakan. Atau mungkin saya boleh coba menyampaikan pertanyaan dari Dr. Damora ya, regarding to the what percentage of the accuracy value obtained from the simulation? Maybe Mr. Inigo.
Yeah, so simulation, normally, you cannot predict 100% accurate. But that is very difficult because it's all numerical methods, calculation, matrix inversion, and some round of numerical values learned. But to be precisely whatever if your inputs are correct, and you can rely on your output. But normally what we have seen is cases like 95% accuracy, and even in additive, some areas we are seeing 99% accuracy. So it depends on the loadings you give, the settings you give, and the material properties you are getting and you are giving. So it's all depends on these parameters. But in overall, approximately, or tentatively, I can say based on my experience, I am seeing in this industry close to 95 to maybe 98, 99%.
I see. Okay, that's good.
So Santosh, you can add from additive perspective if you have any points to add on the accuracy.
Yeah, when it comes to additive, so we talk about high precision and high accuracy. So there are a couple of calibration methods where we can go till 0.1 mm accuracy. So I can call it as 95 plus always. So majorly we want to predict the trend and the distortion which is higher than 95%. So it can be predicted because the overall advantage in additives, we can capture the more variables even in the physical printing process. So that makes any FEA tool to predict result very accurately. So our inputs are very accurate in additive manufacturing, so that we can expect high accurate results or correlation between physical and simulation.
I see. Okay.
We have a couple of case studies on medical. Good that you bring that topic. So in fact, we did 2 implant printing, which is critical, like complete hip socket replacement and joint replacement implant. I think that will be interesting for the further discussion, maybe in the next session.
Yes, sure. Very interesting. Okay. Any question? Ada yang ingin ditanyakan? Kita masih ada waktu sekitar 10 menit. Maybe regarding to the support of the MP software and Simofec, if they find that we need this software, most probably we need also supporting from your side, especially to guide us or to connect us with the industry, not also in Indonesia, but all over the world, so that we can develop our performance to use this software. Is it possible also to connect us with them in any project or something else?
Yeah, so Pak Didi, do you think we see any our customers we can get some project or some collaboration, or what is your thinking on this?
Yes, The first is MTRES and MSc will support UPN VJ to get the maybe as a trainer level of the software. And then MTRES will need UPN VJ to support as a specialist, a technical specialist for first in the Indonesian industry, which is actually need support from a university. That's my proposal, Pak Armasa.
Yeah.
Okay.
Pak, see one more thing. I mean, maybe in Indonesia, but in Malaysia and in Philippines and in some places. So what we done is, we proposed a center of excellence package. So that means, we will sign up an MOU, or we can sign some MOU with your university as an industry collaboration. And there will be some, press release, and, we can publish it in our website and, in the local newspaper. So for that, it need a couple of solutions from MSc, and, the kind of, the offering, or, I work with Pak Didi on the proposal. And it is called the Center of Excellence package. So that, in Indonesia, so your university or your division, your mechanical will become a center of excellence for industry collaboration with MSc. So wherein, we can keep our logo there, our MSc thing. And yearly once or semester wise, you can conduct a workshop, and we will give you additional licenses for workshop, and we will give you a trainer or a speaker from MSc industry along with your own faculties. So we can plan some 2-3 days or 5 days of industrial training. So these all are, couple of engagements, we can work in that line. So if you are keen on, the Center of Excellence package, I mean, so you let us know. So we can explore that option as well. So that everything in MSc solutions will be the resource, the tool, the software, and infrastructure will be there. And your medical team can come and tap, use this technology. Your civil engineering can use, the fluid dynamics guys can use, aerospace guys can use, automotive, and your mechanical, of course. So that one thing, maybe we can think of it, so that, that will differentiate your university in Indonesia, the first one to be a center of excellence in the country.
Right. Thank you very much for the initiative, Mr. Inigo. I will bring this idea and initiative to our discussion in internal discussion in our side. It's very interesting if we can do collaboration, different industries and companies, also Indonesia. But I believe in Indonesia also there are a lot of problems that we have to solve in terms of engineering side. Therefore, we as an academic, we need this collaboration or supporting from the software to become to become as an partners, not also between academic, but also in the industry and all over the world also. Okay.
Yes. So I can just maybe I can just show you once, just 1 minute.
Yes, sure, please.
Just one minute, because anyway we have 5 minutes. I'll just show you.
Okay, no problem.
Yeah. I want to show you some similar cases, or something we have done recently. I'm sharing my screen. Are you able to see my screen?
Not yet. Not yet.
Yes. See, this is
Now,
this is one thing,
yeah.
you know, it's in Philippines basically, you know, so you can see my I am standing this side, so this is basically a center of excellence. So this is the university called the Fiat University, and it is one of the aerospace leading university in Manila. And this is the owner of the university. His name is Mr. Segovia. And then these all are lectures and HODs and department head. And this is from MSc management side. So, you know, you see so this is the press release, you know, there's a center of excellence in Philippines, and they will have a, you know, our logo in the laboratory like CAE lab or, you know, the practical lab. This is one thing. And then it came in all the newspapers and everywhere. So MSc Software Inc.'s partnership with the Fiat. So like this, no, we can do something for your university. Once we have some budget and some kind of, you know, then you know, there is a spokesperson, we talked about, you know, this thing, and the university, they talked about, there is a press release actually. So this happened. Then there is another one. So like this, you know, so we have done similar things to even in Malaysia also. I'm just trying to find out the Malaysian university names. Just recently we have done university. Yeah, just give me a minute. Let me find the Malaysian university one. That also we have recently did some partnership with them.
Okay. Okay.
I think it's UITM or something, if I remember correctly.
Later by email, we can forward to Pak Armansyah and Pak Damora, Trini.
Yeah, yes.
Yeah, Trini, is that UITM who presented
Yeah.
paper in the conference?
You have something to show them?
You say UITM, right?
Yeah, some collaboration, something, you know, which recently we published in with the collaboration with the UITM. I'm not getting the thing because it's handled by my other colleague. One of my colleague, he is based out of Malaysia. So you know, the similar to one which I shown in Philippines, because Philippines. So this is how, you know, we do collaborations with this thing, and I am very keen and interested to, you know, work with your university. Something like a center of excellence like this, you know, not just buying one or two software and license and, you know, which, you know, any universities will have. Okay, maybe one or two license of this package, that package. But something like a partnership or something like, you know, the center of excellence will, you know, differentiate or, you know, will show a uniqueness of your university as well as our MSc. So let's see if possible for that. Otherwise, you know, even I will be happy, even at least let's start, maybe begin with the SUMOFACT first, and then, you know, one by one software technology to your university, and later we can think of it. Or if you have, you know, your management also very clean and very visionary, and, you know, trying to focus this area, and we can also, you know, do something like this.
Okay.
Thank you very much. Thank you.
Thank you very much. Oke. Saya rasa itu ya, Pak Didi ya. Mungkin kita akan diskusikan kembali nanti di sesi selanjutnya. Karena waktu sudah selesai, jadi mungkin sampai sini saja sesi kita hari ini dalam webinar hari ini tentang simulations, MSc Software dan SIMFACT. Insya Allah mudah-mudahan ini bisa bermanfaat buat kita semua dan bisa kita diskusikan kembali ke topik-topik selanjutnya, insya Allah. Baik, Pak Damura, saya rasa kita akhiri ya, Pak.
Iya, Pak. Close aja, Pak, di closing.
Nanti kita diskusi kembali, Pak. Baik, kalau begitu saya mohon diri. Thank you very much for Mr. Sandip, Mr. Trinitor, and Mr. Santos for the presentation. And juga for Mr. Didi and the MTRES company, dan juga kepada semua mahasiswa dan teman-teman yang bergabung di sesi ini. Saya akhiri. Terima kasih atas segala perhatiannya. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera dan salam sehat. Terima kasih.
Waalaikumsalam warahmatullahi wabarakatuh. Terima
Waalaikumsalam.
kasih semua.
Thank you
Thank you. Bye.
Bye.